So yeah, thanks for the opportunity for tailing on some results from Afar onto these exciting results from Iceland. So the work I'm talking about has been going on in the context of a few projects, particularly the Afar Rift Consortium and the RiftVolk Consortium, which are both big international collaborations, and the work involves many collaborators. So I just want to recognize many of those collaborators, particularly those circled in red, particularly colleagues from Addis Ababa University, and also Carolina Pelli and Chris Moore, who defended his PhD last week, and a lot of the results later on in this talk are from him. So here's Afar in Iceland on the same scale from a paper we published nearly 10 years ago now, and you can see that in many ways there's some features in common. So they're both plate boundaries that are extending at around 2 centimeters per year. In Afar, we're in a triple junction, but a lot of the activity is along the boundary between Nubia and Arabia here. They're both influenced by hotspots, of course, but I think the main difference is that obviously in Iceland, you've got a mature system, been rifting for many millions of years. And in Afar, people argue about whether it's the onset of seafloor spreading or it's the final stages of continental breakup. But I think that the important thing from my point of view is that the processes we see are quite similar to the processes that have been going on in Iceland, and also some of the processes that go on the seafloor. So there's two bits of this talk. I'm going to give a very whistle-stop tour of some of the styles of rifting episodes that we've seen in Afar since the year 2000. And then I'm going to talk about what's been going on in response to the Dabahu rifting episode, and talk a little bit about long-lived response signatures to rifting episodes. So it's really been an incredibly active place in the last 20 years or so. Not only activity along the rift boundary, but also we had big eruptions in places like Nabro, and several eruptions in the Red Sea and the Gulf of Aden as well. I'm just going to highlight and move from north to south and talk about the main episodes that have happened along the plate boundary itself between Arabia and Nubia. Starting in the north in 2004, when there was a relatively small dike intrusion in Dalol. This was an eruption. There was no eruption, associated with this intrusion. It was about a 9-kilometer intrusion, we think triggered by a magnitude 5.5 earthquake on this fault that you can see in the 3D model. There was about 0.06 cubic kilometers of intrusion, and some of that you can see in the deformation data. This little pattern at the northern end of the interferogram is very consistent with subsidence associated with a magma, a relatively shallow magma source there. But that can only account, if you do a pure moment balance, it can only account for about 3% of the volume. If we move south by about 40 or 50 kilometers from Dalol, we get to Alu Dalafila, where there was a fairly substantial eruption in 2008, producing something like a 10-kilometer long lava flow. This eruption was nicely monitored by INSAR data both before and after the eruption, as well as seismicity data. And the really interesting thing here was that the data requires a really shallow magmatic source, and it seemed to be segmented as well. So the inversion that Carolina worked on here had this kind of segmented sill opening only at about 1 kilometer depth, and you really need it to be that shallow because of the narrowness of the geodetic source. That fed a small dike that then fed the eruption. And so here again, we're talking about relatively small volumes, but the behavior here we speculated was similar to both in geometry and behavior to what's going on at fast spreading ridges, despite the relatively low spreading rate here. If you move to the most recent activity, again moving south to Ertorales itself. So Ertorales had a very long-lived lava lake, but in 2017 there was an eruption about 3 kilometers to the south of the lava lake and some fissure opening. And the interferograms here show contraction during the period of the eruption around the lava lake itself, and expansion to the south. And Chris, as part of his PhD in a paper published in G-Cubed a couple of years ago, was able to model that with contraction of a dike-like source underneath the lava lake itself, as well as then this shallow dike intrusion that then fed towards the eruption site. One of the, I think the most interesting things here is you can use the radar to also monitor the level of the lava lake itself. So prior to the eruption, the lava lake was full. It was right up at the brim. And then during that initial eruption, it dropped by nearly 100 meters, 90 meters or so. And then that lava lake rose up and then dropped down. And at the same time, in that initial intrusion, obviously the dike further south opened up, and this is the surface displacement data time series of a few points from INSAR. It opened up, and then the opening of that dike mirrors that lava lake height. So we think there's a hydraulic connection potentially between the lava lake and the dike, at least for this time period. And it's somewhat reminiscent here in this case of activity in the East Rift Zone in Hawaii. I think the most spectacular rifting episode, though, I think, and the one that got me involved in working in Afar was the Dabahu episode that began in 2005. This is still my favorite interferogram, incredibly spectacular deformation field that we saw in this MVSET interferogram. So just for scale, this is 100 kilometers across. This red line is about 60 or 70 kilometers that marks the extent of this major dike intrusion. Each of these interference fringes is about 3 centimeters of ground motion. And this was associated with a small rhyolite fissure eruption. There's some people for scale on the side there. Spectacular eruption in itself, but actually was dwarfed by the scale of the dike intrusion. If you just zoom in on that interferogram, you can just see the richness of this geodetic data set, a lot of incredibly dense interference fringes there, lots of ground movement. To cut a long story short here, we were able to model that deformation, create a 3D displacement field from the radar data, and that was consistent with a dike intrusion that was about 2.5 cubic kilometers. So a very large amount of magma was required, large amount of opening was required, all within the upper 10 kilometers or so of the crust, which opened by about 10 meters. About 0.5 cubic kilometer, we think, came from these northern magma chambers at Dabahu and Gabho. You can see the subsidence there. We also think that there was additional materials fed from the segment center. And this was the first of what ended up being a sequence of 14 dike intrusions, which you can see in this next figure. So the upper left panel is a plot of the depth averaged opening along the segment from north to south. So this orange pattern is the opening that happened in that initial 2005 dike. And then we had the sequence of another 13 dike intrusions, each of which is represented by one of these colored slugs in this diagram. And you can see that those are much, much smaller. They typically open by 1 or 2 meters. And they also oscillated up and down the rift. We also know from seismology that they were largely fed from the segment center. You can track the earthquakes. This is a beautiful result from Manolo Balachu, published in 2011 from one of those dike intrusions. And you can see this is time versus a position of the earthquakes, and you can see how they propagate through time along the rift relatively rapidly. This dike intrusion sequence was incredibly reminiscent of what happened in Kraplo in Iceland from 1975 to 84. And so again, this is a comparison on the same scale of the 2 rifting episodes, both of which began with a pretty large dike intrusion and were followed by these sequences of later smaller intrusions that kind of bounced back and forward along the rift zone. In both cases, we had some basaltic eruptions later on in the sequence. These were more voluminous in Kraplo than they were in Afar. And you can explain a lot of what we saw in terms of this oscillation with a relatively simple model that Roger Buck proposed in 2006. We've also got comparisons of earthquakes, and you can look at all this data in the 2012 paper. But again, you can see that a very, very similar pattern of dike intrusion in terms of the time extent and spatial extent of each of these later dikes. So they're essentially propagating at around walking pace. So the bottom line from that first part, we had quite a variety of styles of rifting in Afar in the last 20 years. Let's look at what happens after rifting episodes now in the second part of the talk. So after the Kraplo rifting episode, There was some nice work by Gillian Fulger in the early days of GPS that showed there was this accelerated rate of motion, and they were able to model that accelerated extension that was ongoing after the rifting episode using a simple viscoelastic model. Also, after the 1978 rifting episode in Djibouti, we also had an accelerated period of deformation. So the extension rate here is about 20 millimeters per year on average, but this was up to 65 millimeters a year and then slowed down to about 17. And Kat Anatol interpreted this change in slope as a change in magma supply. So there remained a bit of a question about, is it magma supply that's governing the post-rifting activity, or is it viscoelastic relaxation? So we thought Afar was a good opportunity to see that. And we also see
10 minutes now, Tim.
Great, thank you. And we also see an incredible acceleration and a response in the crust in the geodetic data following the Afar rifting episode. So this is work published by Carolina Pagli in 2014, showing the velocity field from 2007 to 2010 with the elastic displacement from the individual dikes removed. And you can see both in the east-west velocities and in the vertical a very accelerated larger signal than you'd expect from the background plate rate. In fact, the rift perpendicular signal in this time period is about 110 millimeters per year, again, compared to that 20 you'd expect from the background rate. The vertical, something like 80 millimeters per year of uplift. Chris Moore, in his PhD, and there's a preprint of his paper available online as well, has revisited that the area, looked at the current rates or the rates over the last 5 years measured with Sentinel-1 INSAR, and again you can still see this anomaly around the location of the Dabahu rift. The rate of extension has dropped to around 45 millimeters per year in terms of the extension, and the uplift down to about 30 millimeters per year. So Chris has had a go at trying to explain that the full space and time history of deformation, and we like to try and do that with as simple a model as possible. We can't find a simple viscoelastic model that does it without requiring an additional magma sources. So what Chris has done is set up this model using Relax, and it has an elastic lid over a viscoelastic substrate. He's imposed the opening from dike sources that we know about, and then inverted for sill sources at the known magmatic centers, and try to find the best fit rheological structure and magma histories that match the 4D displacement histories. So this is a rather complicated diagram, but the data, this is just a subset of the data that Chris has been matching. So the data on the left here, it consists of here a sequence of for the INSAR tracks, and for each of those you've got a time history, and they cover different time periods and different geometries, and you can look at profiles through those. These are the model fits then as well in the center, and the residuals, and you can see particularly from the profiles here for different time windows, we're doing a fairly good job considering how simple this model is at fitting this complicated 4D displacement pattern. What you need to do that is both magma and viscoelastic relaxation. You need a viscosity of around 10 to the 18 Pascal seconds under an elastic lid that's about 20 kilometers thick. We've only allowed uniform viscosity here, and I think there's some hints in the data that some time variation in that viscosity or some depth and spatial variations would obviously help fit the data. But you also need significant ongoing magma movement, both initially during the major activity of the dikes here, but also ongoing activity, particularly at Ertorales in the center of the rift segment. So just to conclude, so Afar has been incredibly active for the last 20 years. Rifting episodes have shown a wide variety of behavior, and I think we've learned a lot, I think, from comparing things to Iceland, and particularly when we were looking at the Dabahu rifting episode, the similarity to Krappler was uncanny in many ways. Large rifting episodes have these long-lived signatures, and we need long-term observation strategies to capture these important data sets. So relatively simple models combining viscoelastic relaxation and ongoing magma movement can explain most of the things we see in the geodetic data. So I will leave it there. Thank you.
Excellent. Thanks for this talk. There's time for a few questions. So far, there's none in the chat, and I can ask my own. You mentioned that in Ertorales there was a region of compression. How did that happen? Why is there compression in an extensional system?
Okay, so let's find the figure. Let's see, I can find the figure. I just sent a message 7 to the chat by mistake, which was me trying to go to slide 7. It was slide, but there we go. So this is the relative situation of what's going on during the dike, during the instant of the dike intrusion itself. So overall, we're in an extensional setting, but what's happening is that the magma is leaving a source around the lava lake, and the draining of that magma, the reduction in pressure there is effectively bringing the sides in. So essentially, it's a reduction in pressure in that source and an increase in pressure in the source along the rift. So it's a relative change. I think overall you're still in extension. Yeah. If that makes sense.
It's a bit like this chicken and egg question, whether the caldera collapsed because the dike is propagating or the other way around. So
yeah, I mean, ultimately the tectonic stresses, I think, guide everything, right? So you're pulling the source here, but Ertorales is kind of oversupplied with magma. There's a lot of magma there, so the magma I think helps trigger these things.
Right. Any other questions? Suzanne has a question.
Well, maybe a question, Knut Rodnason from Iceland.
Do you go ahead?
Sorry? Sorry?
Yes, please ask a question. It's time.
Yeah. Well, the Silali in Kenya, it's a huge caldera, and nothing came up as far as I understood or stand in that caldera formation. Have people studied that? It seems to me could be sort of somewhere between the Afar rift and Toro and Parlabonga.
Yes, so you're talking about, I missed the first location of you're talking about Kenya, did you say?
Yeah, it's in Kenya.
Yeah, so I think there's been a lot of the recent activity, recent work, particularly by Juliet Biggs and other colleagues in Bristol, have been looking further down the East African rift. So I'm really trying to understand that kind of sequence of, trying to treat the variation we're seeing along the East African rift potentially as the variation we're seeing in space is potentially relating to a variation in time in terms of how we might progress from the initial stretching of crust through to full seafloor spreading. So Juliet, I don't think she's online, but she would be better to answer questions about the specifics of that than I would. But I think there's a lot to learn, I think, from looking at these spatial variations in the magmatic systems along the East African rift. I'm sorry, I didn't answer the question fully.
Suzanne, I think it's good if you ask your question as well, because Tim started a bit late and it's unfair if we cut now at 5.
Sure. So Tim, one thing I was wondering about a bit, or say I was intrigued about, is this the similarity you see between the Afar and Iceland. So does that then mean that the system is mostly, from a rheological sense, that the system is mostly determined by the magma and brittle behavior in an extensional environment? Because the overlying material is different in both settings, right? In Iceland, I mean, Iceland is not granitic, it's not a continental material, whereas Afar is continental material. So when you say the similarity, is that from a rheological perspective, then mainly driven by the magma and brittle behavior, or what's your thoughts about this?
Yes, I think depends where you are in Afar, I think, what the structure is. So I think my prejudice is that when you are right on the rift axis, you've probably had, maybe a few million years of diking here, or certainly hundreds of thousands of years of diking. So maybe locally, actually, you're in a very specific situation here of a kind of basaltic type crust that is much more like Iceland. But I think overall, this is a system governed by the dynamics of the of the magma, of the fact you've got an oversupply of magma because of the hotspot, and you've got a similar extension rate. And I think there are differences. I think there's more silicic magmatism in Afar is one of the main differences, but there is silicic magmatism, of course, in Iceland as well. But I think there's probably more involvement of incorporation of crustal material, etc., in Afar than there is in Iceland. But yeah, I think the fact that the behaviour is behaving the same way is telling you that, I think, particularly in this case, that it's the magma supply and the interaction of that magma supply and the tectonic stress that's governing the situation.